In this video, we'll be covering section 6.2, regions between curves. We have two objectives. We'll be finding the area of a region between two curves defined as functions of x, and then we will find the area between two curves that are defined to be functions of y. So previously, we have found areas under curves down to the x-axis, area between a function and the x-axis. Now we want to incorporate a second function and find the area between those two functions. The process for doing this is really the same as before. So we're going to take the interval that we're looking between, divide it up into a bunch of subintervals, and form rectangles inside of those subintervals. The heights of the rectangles now will not be determined just by one function, but by both functions. So the distance between the two functions will give us the height of each of our individual rectangles. As before, the width of them, we're going to use the equal width between each one. So delta x will be the width of the rectangles, which will still be b minus a over n. So if we take a typical rectangle that we're going to have from this type of partition, then we need to figure out the dimensions. So we've already said that the width is delta x. The height of the rectangle, though, is going to be the difference in the function values. So you take whichever one the upper function value is, and in this case f of x is the upper function value, and you subtract off the lower function value. So f of x minus g of x would give us the height of this rectangle. As before, the x sub k stars are just representing our sample points from each of the individual subintervals. So the area of just one rectangle is going to be the base times the height, which would be delta x times this difference. So this is what each rectangle, the area of each individual rectangle, would be that expression. If we want to get an approximation for this entire area, then we simply need to add up all of our different rectangles. So if we want to improve the approximation to get the exact area, then we simply need to increase the number of subintervals, or in other words, increase the number of rectangles. So if we take the limit on this as n goes to infinity, then that will give us the exact area. But this is precisely a Riemann sum, so if we take the limit as n goes to infinity of that Riemann sum, it really is just an integral. And the way to interpret the integral is we are integrating the upper function minus the lower function. Whichever one is above minus whichever one is below. So that's rewritten all here. So if we have over an interval AB, if f of x is always greater than or equal to g of x, then the area between those two functions is always the integral of the upper function minus the lower function. Now, in some sense, this is what we were doing before. So that's what this quick check is actually referring to. It's saying, suppose that you have your lower function is just the zero function, then how would it work in this case? Well, make a little rough sketch here. So let's just say this is our function y equals f of x, and then if we think of our second function as just being the zero function, then according to this, the area is going to be equal to the integral from a to b, just put in arbitrary a and b here, from of f of x minus g of x dx. But this is really 0. So if it's 0, it could just be wiped out. This is going to be equal to just the regular definite integral, which is what we did before. So that would still give us the area in this region here. So really we were doing it before. We just didn't have to worry about the lower function because the lower function was always the x-axis before. So this is really just a generalization of the way we were doing our problems before. Okay, so let's try one. So this says find the area of the region bounded by these two graphs. Now with many of these problems, you are going to be given just the two functions. You are not going to be given a picture. So it would be helpful if you could quickly make a rough sketch of them. Your knowledge of transformations and the basic parent functions will come in handy here. So for example, if we were going to graph this function, we know that it's an upside down parabola because of the negative sign here, and it's shifted up 5 units. So we could draw a rough sketch of what that would look like. Similarly, this is a parabola shifted down 3 units, so we would get the sketch of that. The benefit of having that knowledge is you can easily identify which function is the upper function and which one is the lower function. The other thing that we need that's not immediately obvious is we need these 2 points. They will typically not be given to you. You'll just be given this. So this is where the 2 functions intersect each other. To find those points, then we need to solve the equation f of x equals g of x. This will be true in general. If you want to know where 2 functions intersect, just set them equal to each other. All right, so we just have a small algebra problem here. Move the x squared to the same side. I'm going to go ahead and subtract the 5 as well. So you have 0 equals 2x squared minus 8. We could divide everything by 2. And then you see we have a difference of squares. So this is where we get the plus and minus 2. It's where we get these coordinates. If for some reason we needed the y coordinates, you would take this and plug it back into either one of the 2 functions. Okay, so we know where they intersect. We know which one's the upper, and we know which one's the lower. So we can go to the area integral then. So area is equal to the integral. In this case, what you want to think of is how your rectangles are drawn. So for now, they've always been drawn vertically, but later on we're going to start drawing them horizontally. When you draw your rectangles vertically, the way I think of it is you're taking this region and you're slicing it up. To form those rectangles, we are slicing perpendicular to the x-axis. So that tells us we are integrating with respect to x. We've always been doing that up to this point, but that is something that is going to change. So we're integrating from this x value, -2, up to +2. And then we do upper. In this case, the upper function is 5 minus x squared minus the lower function, which is x squared minus 3. And that is with respect to x. Okay, so before you integrate, you could integrate right now, but it's going to be much better if you simplify this first. You'll have less things to plug in. So if we simplify that, looks like we get 8 minus 2x squared. One other thing to notice, something you don't have to do, but this is an even function, right? This new integrand here is even, so, and this is a symmetric interval here, so we could actually simplify this further, because anytime we can use 0, it's preferable, makes it easier to plug things in. Okay, so we get that. So now let's integrate. So we have 8x minus 2/3 x cubed. And then we just have to plug in the limits of integration. So let's go ahead and do that. We'll leave this 2 out here in front. If we plug the 2 in, we get 16 minus, this will be 8. 2 cubed is 8. Multiplied by the 2 is 16/3. And then gotta be careful with your grouping symbols here because the 2 has to be applied to everything. So then when we plug the 0 in this case it doesn't do anything, so we don't have to worry about it here. Okay, so get a common denominator. So this will become 48/3 minus 16/3. Let's move this down. All right, so when you subtract that, you end up with 32/3, and then if we go ahead and multiply that, we get 64/3. So that is the area of the region between those 2 functions. 64/3 units is this region. Okay, the next quick check says interpret the area formula when written in this form. So, and it says assuming that f is greater than g, they're both positive. So the picture would look something like this over the interval ab. Well, if we look at the first integral, this picture is modeling what you see in the first integral, the integral from a to b, f of x dx. That represents the area between the function f down to the x-axis. If our goal was to find the area between them, then this is overcounting. It has too much. If we look at the second integral, it would be represented by this green region down here. That would be the integral from a to b, g of x dx. So we can see if we took the difference of these two, as it says here, it is going to give us precisely the region between them. It's just a different way of kind of seeing why the formula works. We can also come back here and apply the properties of integration that says if you have the difference of two integrals over the same interval, you can actually combine them into one integral. We usually do this property in the reverse direction, but it also could go in this direction. And this was the area formula that we had before, integral of the upper function minus the lower function. Now, they specified to restrict to this case where f and g are both positive, and that f is above g, but we can actually do this in all cases. So here I have f is still positive, but g is negative. If you look at the first graph here, this would be the integral from a to b, f of x dx, just like before. And this one down here is, again, the integral from a to b, g of x dx. The difference is, in this case, that this function is actually negative. Our goal is to get the area between the two functions, and so because, as we said, this one is coming out negative, if we write the expression, the integral from a to b, f of x dx, minus the other integral from a to b, g of x dx, then the fact that this is already going to come out as a negative area, and we put this negative in front of it, makes it positive. So in effect, this will actually add these two areas together. So even in this case, it still works. It does what's intended. All right, the final case we could look at is, suppose they're both negative, and the goal is to get the area between them. Well, we could start with this area. This is the integral from a to b. Oh, sorry, this is not f of x. I switched it on you. This one is g. And then this one is f. So if you integrate this, this is going to come out negative, and we don't want it to be negative. So we're going to put a negative sign in front of it. This would actually represent this area as a positive number. The blue area you see here, we don't actually want that. We want to remove it. So we want to subtract this from this. But since f of x is a negative function here, this is going to come out as a negative number. So by adding this to this expression, we would actually get the area between them. So this expression does represent this area. We can reorder this though and combine the integrals, and we get back to the same expression that we've had for each of them. So the point of this is, it just doesn't matter. You can always do the upper function minus the lower function, whether they're positive, whether they're negative, and even if they switch back and forth being positive and negative. As long as you always have the same function on the top, the same function above the other one, then the process will always work. Okay, so let's try a different one. In this one, what makes this problem different from the previous example is we actually have changing boundaries. So we're using this absolute value function, but we don't actually have a way to integrate absolute value. So what I mean by that is, we could represent this as the integral from some a to b, we'll find these points in a minute, of upper function, which would be x plus 2 minus absolute value of 2x dx. This would represent this region. The problem is I don't know how to integrate absolute value. Your calculator can do it, but it only does it as an approximation. So we have to come up with a different way of representing this. And so the way to do that is to break down what the absolute value of 2 really is. It's two linear functions. On this side, it is just 2x. It's just y equal 2x here. On the other side, it's going to be y equals negative 2x. So then what we think of as happening here is we actually have a changing boundary. On this left-hand piece here, the upper function is f of x, but the lower function is this expression. And then over here, it changes. The upper function is still f of x, but the lower function is now 2x. So we're going to have to do this as two separate integrals. Now we also need to find these points. They are relatively obvious from the graph, but you may be doing rough sketches by hand, so they may not be so obvious. We find those points doing the exact same thing we did before. Set this expression equal to that to find this point. Set this expression equal that to find the 3. I'll let you do the work to verify that it is -1 and 3. So let's go ahead and write down our area integral. So the area will be the first integral, which will be from -1 up to 0. We're slicing this thing starting here at -1, and we keep slicing it all the way up to 0. On that piece, the upper function is x plus 3. Lower function, minus -2x. Remember, this minus is built into the area formula that we're using here. Upper function minus lower function. This will give us just the area of this piece here. Okay, so then move on to the second one. That one will be from 0. We're start slicing here, and we slice all the way up until we get to x equal 3. And upper function is still x plus 3. Lower function is now just 2x. All right, we simplify each of the integrands. So this negative is going to cancel here, so you do get 3x plus 3 on the first one. And on the second one, we're going to get 3 minus x, looks like. Antiderivatives, you've got 3x squared over 2 plus 3x. And the next one, you have 3x plus x squared over 2. All right, I'm going to spare us the time of plugging all of this in, but one thing to notice, here you have to be careful because we're used to plugging in the 0 last, but on this one, you always plug the upper limit in first. So 0 actually gets plugged in first, and then you subtract plugging in this number. So you have to be very careful with your signs on that. So if you put everything in and simplify, this should come out to 6. Okay, so suppose we have functions that are no longer defined in terms of x, they're defined in terms of y. So notice these graphs here, they don't pass the vertical line test, but if we rotate them, let's change this to the arrow, then if we rotate them in this direction, now they do, each of the black curves there do look like functions as we would think of them. So we're going to do basically the same process, except instead of dividing the x-axis up, we're now dividing the y-axis up when we make our rectangles. So we're going to integrate along an interval along the y-axis, along here. So we'll slice this up and make a bunch of rectangles like this, but you still have an upper function and a lower function. The way you have to look at it, though, is you do kind of have to rotate your head. And just to simulate that again, you rotate your head like that, and when you look at the picture, you can see this will be upper and this will be lower. So the one that is further above the y-axis is the upper, and the one that's closer to the y-axis is the lower function in each of those cases. So other than that, it's going to basically behave the same way as what we were doing before. So you could write this whole thing out using a Riemann sum, taking sample points along this y-axis, but this notation really is the exact same thing. We're just now integrating with respect to y instead of with respect to x. So let's try an example of this. Oh, actually, this is just formalizing that statement. This is showing you a typical rectangle, same thing as what we did before. Okay. So again, same type of thing as before. These graphs are provided in your notes, and some of the problems may give you the graphs, but you would be responsible for being able to graph these functions. So our knowledge of parent functions is going to be useful here. So I've graphed the cubic function. Remember, the key points for that are these 3 key points. And then if you needed more points, you could just plug in extra values to it. So, and then the line, y-intercept is 6, slope is 1, so you get a rough sketch of that. This point, if you needed to find it, you would set these equal and try to solve that. This would be a cubic, be kind of messy. You could solve it using rational root theorem or just guessing at numbers until you hit it. Most of the ones that I give you, you should be able to solve their intersections fairly easily. This would be a little bit messier one. Okay, so one other piece that we have to look at is what is the region that we are bounding here. So it is bounded by these two curves, but we would need one more curve to bound them, and that's where the x-axis comes in. So this is the one that actually closes it off. And so the region that we are actually finding the area of would be what's in here. All of this. Okay, now this problem is one that we can actually do multiple ways. We can integrate it with respect to x. We can also integrate with respect to y. And we're going to show both of those methods. It's good to be able to see how they both work. In some situations, one will work out better than the other. But let's start with integrating with respect to x. So the way I visualize it is I visualize what a typical rectangle would look like. So if you were slicing this thing up to make rectangles, they might look like that. What this does is it helps you identify upper function and lower function. But notice, as that rectangle moves across the shape, the boundaries change. So if I were to draw the rectangle in here, the upper function, it's still the line, but the lower function is now this cubic, where over here, the lower function was just the x-axis. So that indicates that we're going to need to do two separate integrals. So we'll start with this triangular region here. That would be the integral from -6, that's where we would start slicing, and it would go up to 0. On that interval, the upper function is the line, so it'll be x plus 6 minus just the x-axis, which would be 0. Technically, you don't even need to write that. So that's going to give us this region just in here. Okay, then to get the second one, we'll do the integral from 0, starting here, and slice it up to 2. And on this one, again, the line is still the upper function, but the lower function is the cubic function. Okay, so then you could evaluate this integral. It would give you the area of this piece and the area of this piece. It looks like that comes out, this one here comes out to 18, and this one comes out to 10. So the whole thing comes out to 28. Okay, so nothing wrong with doing that, but it was a two-step process. The more steps that we add, the trickier things can become. So let's clear this and try it a different way. So if we go back to our region, let me put the boundary in here again. And if you imagine turning your head to the right, where this can be viewed then as an upper function, and this is viewed as a lower function. So our typical rectangles, if we were slicing horizontally, would look something like that. And no matter how I draw that rectangle, no matter where I slice along this way, this green curve is always the upper, and this is always the lower. So the benefit here is there is no change in the boundaries. The boundaries are always the same. This is always upper, and this one is always lower. So it is preferable for us to integrate with respect to y. Again, the way we can see that this is integrating with respect to y is that I'm slicing up the y-axis. When I make these rectangles, they are perpendicular to the x-axis, so that's how we're slicing it up. Okay, now in order to do that, we would need to write these as functions of y. What that means is you just need to solve these for x. So the line's real easy. Just subtract the 6 over. So this line is really x equals y minus 6. That is the same as this function here, just solved for x. Do the same thing with this one. This is the cubic function, but if we solve it for x, it will become x equals y to the 1/3, the cube root function. So the cube root function is the upper, and this line is the lower. So our area can be expressed as the integral from, now here's where you have to be careful too, to look at our limits of integration. We are slicing up the y-axis like this, and we slice all the way up until we get to this point. So that means we are slicing from here to here. That's where all of the rectangles are being constructed. So it's an integral from 0 to 8. And then upper, y to the 1/3, minus lower, which is y minus 6. So that whole integral, rather than doing it in two pieces, we can just do it in one single integral. So if we go ahead and take the antiderivatives here, this is going to become y to the 4/3 multiplied by 3/4. Right? We're dividing by the new power, which brings it up as a reciprocal here. And then it'll be minus y squared over 2 plus 6y. If we start plugging in, we have 3/4 times 8 to the 4/3 minus 64 over 2 plus 48. We don't need a calculator, we can do this. So this is a cube root. Cube root of 8 is 2, and then 2 to the 4th is 16. So you have 3/4 times 16 minus 32 plus 48. You can cancel a factor of 4 here, so this is really just 12 minus 32 plus 48. That comes out as a negative 20 plus 48, and you can see we get the same final answer as the previous one. We still get 28 units. So it's definitely helpful to be able to see both types of integration. I think both are illustrated actually for you in the notes. All right, let's do another quick check. So the quick checks in this section are particularly good, I think. This is a nice one because it forces us to draw the graphs ourselves. So we have to construct the region bounded by square root of x, the line y equal x minus 2, and the x-axis. And then we're going to express the area in two different ways. We're not actually going to find it on this one. We're just going to express it in two ways. So let's see if I can actually graph these nicely. So square root, we know that its key points are 0, 0, 1, 1, because the square root of 1 is 1, and the square root of 4 is 2. So we just need to connect those. Oops. All right, then the line y equal x minus 2, so negative 2 is here. And positive slope, up 1 over 1. It's going to connect those points there. All right, and then we also have the x-axis. So the region that we're looking at is this region in here. Okay, so let's try doing it with respect to x first. So if we're going to integrate with respect to x, again, think of a typical rectangle being drawn in there. Notice that this rectangle has the square root as its upper and just has the x-axis as its lower. Whereas if I drew one over here, we have a different, the upper's the same, but a different lower. So that means this really has to be broken down into two separate integrals. We can integrate this piece, and then we can integrate this piece over here. All right, so A said integrate, get the area with an integral with respect to x. Let's do that one. So we are integrating, the first one would be from 0 out to 2 of just the upper function. We don't need the lower function because it's 0 on that first piece. And then the second one would be from 2, starting here, and integrating out to 4. And upper function is still square root of x, but the lower function would be x minus 2. Notice how important parentheses are going to be here. That negative would have to be distributed to both. Okay, it didn't ask us to find it, it just said express it. this actually is a common thing on the AP test. A lot of times they'll give you a scenario, and usually it's a pretty messy function. They may even give you a picture for it, and they just say write out the integral that represents the area, but do not evaluate it. So that's all we're asked to do here. We could totally do this one, but we're not asked to do that. Okay, so now we want to go back and we want to slice it in a different direction. So I can't really just erase those easily. So I'm just going to try to draw it in here this way. If we're going to make the rectangles horizontal, then notice that no matter where I put this rectangle, as I move it up and down, this is always upper and this is always lower. Now, in order to integrate with respect to y, we would need to get formulas for these. So we would come back and solve them for x. So add the 2 over, you get x equals y plus 2 is this line. And then for this one, you'd square both sides. So this is x equals y squared. Technically, it's just the upper portion of x equals y squared because the full graph of x equals y squared would be the parabola. Okay, but this is upper and that's lower. So we're going to do the integral. And again, now you have to pay attention to your limits. We're slicing it like this. We start here and slice it all the way to this point. So it's an integral from 0 up to 2. Right? That's the interval that we're actually integrating y over. So 0 to 2, upper function is y plus 2 minus the lower function, which is y squared. Each of these integrals should have the exact same value. Now, you might be seeing that there is a different approach that we could take for that one, and we will see that in something similar in the next example, so I'll leave that for now. Okay, so this one's already graphed for us. It says find the area of the region in the first quadrant bounded by y equal x to the 2/3 and y equals x minus 4. So it's very similar to the previous one in that if we were going to integrate with respect to x, then we would have two separate integrals that we would need to do. We need to do this integral, and we would need to do the integral for this piece. But there is a different approach that maybe you were thinking on the previous one, and that is what we could do is we could find the integral of the area under the blue function. Forget the red function completely, just do all of this, and then just remove this piece here. And that would actually, it's still a two-step process, but it would be simpler. So let's write it out that way first. And then we are also going to do the integral with respect to y as well. So there is a lot of different creative ways that you can do these. Alright, so one way to do it would be to integrate from 0 all the way out to this point here. So 0 out to 8 of just the x to the 2/3. Now that's going to give us too much because it's going to give us all the area under the blue curve. So what we want to do is subtract the area under the red curve, but we can only integrate it from, not from 0. Its integral should start at 4 and go up to 8. Alright, so that would work in general, but we can make this even easier because this is just a straight line. So the piece here at the back is really just a triangle, right? That's really just minus 1/2 base times height. And for that particular triangle, the base is 4. I forgot my 1/2. Base is 4, and the height is also 4. So that whole little triangle there is just 8. So really we could do just the first integral minus 8. And that will give us the area. Okay, the other approach would be to, again, go back and integrate with respect to y. This is probably the easiest on this one, but it's still good to see the multiple approaches. So if we were going to integrate this with respect to y, we have to solve these for x respectively. So this thing would end up being x equals y plus 4. And this would be the upper function if we were going to draw our rectangles in horizontally like this. Then this is upper, that's lower. If we solve this one for x, we get x equals, to get rid of that power, we have to take the reciprocal power on both sides. So it would be y to the 3/2. Right? We're really taking 3/2 power on both sides. And on this side, those 3/2 powers would cancel. So this gives us the formula for the upper function. So area would be the integral from, now we're integrating this direction, so it would be from 0 up to 4. And then upper function would be y plus 4 minus y to the 3/2. Okay, I'll skip all the math again here. If you work this out, it should come out to 56/5. The most important thing right now is to be able to set up the integrals accurately. Yes, it's important for you to be able to, mathematically evaluate this, but the most important skill right now is being able to set these up in some, using some correct notation here. All right, that was space provided just for doing the alternate approach. Okay, this next piece I believe was left out of your book, which is a little baffling. I'm not sure why it was not in there. So I think the following examples you won't actually see there. They're just my examples. So sometimes you have curves that one function does not just always stay as the upper function. They oscillate between each other. So you see that in the graph here. The f of x starts off being the upper function, but then it switches over to become the lower, and then it goes back up to being the upper function. Well, we can actually generalize the formula that we had before. To get the area between two curves, no matter which one is the upper or the lower function, all you have to do is integrate the absolute value of the difference of the two functions. Then it doesn't matter which one's upper or lower, because when you draw your rectangle, it doesn't matter if you do g of x minus f of x or f of x minus g of x, because you're taking the absolute value of that in the end, so it becomes positive no matter what. The problem with that is, in practice, if you actually want to evaluate it, we don't have a way to evaluate absolute value. So what you're typically required to do is find these crossover points. Set the functions equal to see where they intersect. Those points where they intersect means that they're changing from being upper to lower, and then do separate integrals on each one. So what I mean is that the overall area there could be thought of as the sum of the three separate areas. And we can write an integral for each one of those. The first one would be the integral from a to c of f of x minus g of x dx. Then the next one, they flipped. So it's integral from c to d over this interval, but now it's g of x minus f of x. Right, g of x is now the upper function. And then the final one would be the integral from d to b of f of x is back on top now. So if you're doing it by hand, this is typically what's going to be required. Breaking it down into separate integrals, evaluating each one, and adding it together. So let's try one of those. I've got two polynomial functions here. We've got this cubic, and we have the quadratic here. And the first thing you would need to do is figure out when they intersect each other. So you won't normally have a graph. You could just be given this with just, the two functions. So to figure out where they intersect, just like the very first problem, we set them equal to each other. And then hopefully they solve nicely. On this one, you can actually see that the x squareds cancel, which makes this one work out nicely. If I just move this over, we get 3x cubed minus 12x equals 0. Factor out 3x, which leaves x squared minus 4. And then this is a difference of squares. So we get solutions of 0, 2, and -2. And those correspond to where these points intersect. So on the x-axis back here, this would be -2. That's obviously 0, and that would be 2. So we can find them even without having a graph. Okay, I'm going to clear those off just so we have more space to write here. Okay, so now we can set up the separate integrals. So we can integrate, first one will be from 0, or sorry, not 0, it'll be -2 up to 0, integrating from here to here. The upper function in that case is f of x. So if you'll permit me, rather than take the time to write out the entire function, let's just write the name of them. And then go to the next piece. We will add on from 0 to 2, but now g of x is the upper function. Alright, so if you actually do this difference, if you subtract those two functions, this function minus this function, you get, looks like 3x cubed minus 12x. And then this one is just flipped around, which means it has to just be the negative of this. So -3x cubed plus 12x. And then you simply integrate both of these. Now, this is kind of a bad example. I probably should have chosen a different function, because it turns out that the each one of these, this comes out as 12 and this comes out as 12, and you might think then that, well, they're just always going to be equal, so just do one of them and double it. Well, that's not true. It worked out that way with the functions that I chose. This area turns out to be 12, and this area also turns out to be 12, but it is not obvious that they would have to be equal to each other. And in general, they don't have to, so don't try using a shortcut like that. There are ways to analyze even and oddness to help out with this process, but for this problem, in general, it's not wise to just make assumptions like that. So again, I'm going to skip the math. Hopefully that's not where we're having our issues. Hopefully it's just setting them up that's the challenge. Okay, now if this was a problem where you were allowed to use your calculator, then you really don't need to do any of this. You can go straight to the answer by just integrating from -2 to +2. No need to break it, and just do the absolute value of one of the functions minus the other one. So for example, if you were using your calculator, store that in y1, store that in y2, and then just integrate this, and it will give you 24. Okay, two more examples just to give you some more looks at this. So these are examples again where you have to graph them, and I picked these mainly because they're written as functions of y rather than functions of x. So if you think about this, if it was written the other way, y equals 3 minus x squared, well, we would immediately recognize this as a parabola shifted up 3 units and frowning. Well, it's going to have the same basic properties with respect to as being a function of y. You just kind of have to turn your head. So that means this is the positive x-axis, so it's going to be frowning like this. So that means the vertex point would be out here at 3. It's shifted up 3 units, but now it's frowning. So if we use our standard 3 points, right, those would be the same 3 points that we would use if it was a regular parabola. Right, regular parabolas, we would start like that, 0, 0, 1, 1, and -1, +1, and we would transform that. So that is what I'm doing with this one, just shifting them up 3 units, right? They would, and I flipped them over. They're reversed. Okay, if I need another point, I know if I go over 2, I have to go up 4. And again, if that doesn't make sense to you, you can just plug numbers in. Plug in a y value, plug 2 into this. You got 3 minus 4 gives you a -1. And then because of symmetry, it would also be there as well. So that is the graph of this curve. Okay, so then the line for this one, it probably is easier just to rewrite it as y equals x minus 1. So we know we're starting down here, and we have a slope of 1. Okay, so roughly like that. Now, to find where they intersect, normally you would need to set the equations equal to each other, but this one worked out so nicely on the grid that we can see where it actually intersects. Okay, so now you need to decide whether you're going to integrate with respect to x or with respect to y. So to do that, you want to try putting in like a typical rectangle. So if I put in one here, this looks good. What I mean by good is you've got one of the curves being the upper and the other one being the lower. So it looks like integrating with respect to x is going to be fine. The problem is when you get over here. On that piece, that rectangle has the same curve as its upper function and its lower function. Another way to describe why this is going to be a problem is the blue curve is not a function of x. It doesn't pass the vertical line test. If it's not a function of x, you're not going to be able to integrate with respect to x. So a better choice is going to be to integrate with respect to y. If I draw in our typical rectangle here, and no matter where I put it, it's always going to have the blue as its upper and the red as its lower. So integrating with respect to y is definitely preferable here. To do that, we need to have this one solved as a function of y. I guess it already is, sorry. They both are. So that part's already done, so we can go right to the area. So the area is going to be equal to the integral. Starting down here, we're slicing it up along the y-axis. So it starts at -2, and we slice all the way up to positive 1. So -2 up to 1. And then upper, as we mentioned, is this blue one. So 3 minus y squared minus the lower one. So this represents the area of the region. So again, I'm going to skip all the math. We should be able to do that. Should come out to 9/2. All right, last example. On this one, we're given a cubic function and then given another parabola. So let's graph the cubic first. Hopefully we remember that the key points are these 3 key points. If I plug 2 into a cubic function, I have 8, which is way off of this. So those are really the only 3 that I can get on here. All right, so the cubic would look something like that. Concave up on the right, concave down on the left. And then we have another parabola. This one is positive, like it's smiling, but it's shifted down. So shifted down means it's going to be down here. Those would be our first 3 key points, and then to get the next one, I'm going to go up to and over 4. So I think I'd be there, and then down to and over 4. And again, you could test those. If you just take y equals 2 and plug it into this, you can see that x comes out as 2. All right, so that's our graph. So the region that we're looking for is this region in here. Now, what makes this one different, if you notice the directions, it says we are approximating, and it says evaluate using a graphing utility. The reason we're going to need a graphing utility is that this point of intersection is not nice. You find it by setting these equal to each other and solving, but we don't actually have a good way of doing that. This one's nice, not a problem here, but this one is not. Okay, before we even get to that though, we need to decide, should we integrate with respect to x or y? So just like the previous one, if we try drawing in a typical rectangle, the rectangle here, drawn vertically, meaning if we integrate with respect to x, that one's good. We got upper function, lower function's a different function. But as soon as we get over here, we have the same type of problem that we had on the last one. The rectangle uses the same curve as its upper and lower function, and we can't have that. So integrating with respect to x is out. If we try drawing it in the other direction, then no matter how I draw those rectangles, we always have one upper function and a different lower function. So integrating with respect to y is going to be the way to go. Now for right now, we're going to write the integral, but I just want to represent this x value. I'm going to call it capital T. We'll find it using the calculator, but let's just represent it with t now. So our area is equal to the integral from -1 up to this t value, which we don't have yet. The upper function would be this. We need to solve that for x. So that gives me x equals y to the 1/3. Right, this is a cube root function when you solve it for x. So we've got y to the 1/3 minus the lower function. That's already solved for x, so we can just plug that right in. Y squared minus 2. Okay, so this integral will give us the value, the area that we need. So let's pull out the calculator now. Okay, so I've gone ahead and entered some of the functions into the y equals. So we've got the cubic function here, but this one here creates a problem. So it's not a function of x. So in order to graph it at all, you have to solve it for y, but you're going to get two different expressions. If we solve this for y, add the 2 over, and then take a square root, you get the positive square root of x plus 2 and negative square root of x plus 2. Then I tried to choose a window that was approximately the same as this window here, and the graph, you get that. So we need to find this point of intersection here. So to do that, we do second calculate, go down to intersect, and then just get close to it on each of the curves. All right, so hit it 3 times once you get close to it. This is our intersection. Actually, that isn't. Oh, sorry. Yes, it is our intersection. Now, the important thing though is that we wanted to use the y value, not the x value. That's the key thing that we have to be careful with here. We're integrating with respect to y, not with respect to x. So this is really the value that we want. Now, I know that the calculator stores this, but I'm not sure if it stores the y. So let's test that. Let's quit out of this and let's pull up y and see if it matched. It did. Okay, so that's very convenient. It stored the y value for us. So this y is actually what our t value is. So if I pull this over, what this tells us is that t is approximately 1.793. And so we just need to take that and put it in our integral. Now we're going to make the calculator do this, so it's going to be best if we just use it as a stored value. So let's go back to the calculator. So it's stored currently as y. So let's we'll type in the integral. So math 9, lower limit's -1. Upper limit we're going to put in as y. That was the stored decimal that you have here. And then we need to type the integral out. Now, unfortunately, well, actually, we can, yes, on the screen, we can use y. It looks bad because it looks like you're using the same variable in 2 places, but it will recognize it as a separate variable because we'll put y here. You could also just integrate it with respect to x, meaning type this whole thing out with x, which is going to be quicker. So let's actually do that. X to the 1/3 minus y squared, or x squared, minus 2, and then with respect to x. So you can type it all with y or all with x, but either way should work, and this gives us the integral we were looking for. So the approximate value for this problem is 4.215 is our approximate area for that region. All right, and that's basically it. This process of finding this value and having it being a rounded value. I have seen that quite a bit on the AP test. So the book probably doesn't do it very often. I don't know that Math Excel has any of them like that, but I just wanted to show it to you because definitely could see that on the AP test. All right, well, I think that concludes everything we have for this section, so we'll see you guys on the next one.